Hi everyone, my name is Matthew Figueroa along with Marco Holero and Evan Peterson. And for the 106 project presentation, the prototype that we bring before everyone is the automated pet feeder. A quick run through for this presentation is that we're going to have an overview which explains the components and the requirements used for this project along with basic context. And then we're going to go over to the component aspect where we explain the role and the code for every component used in this project. Then moving forward, we're going to explain how it works with a demonstration and close it out with a conclusion. So a quick overview of the requirements for this project. We use one microcontroller, which was the Raspberry Pi Pico that was coded with Python, an actuator, which was our 6-volt DC motor, two different sensors, which is the load cell and the ultrasonic sensor, along with the circuits and the mechanical components. The mechanical component was the crank slider mechanism that you can see on the right hand side of the image.
So our first sensor was the ultrasonic sensor. We used the library that we were given in class and wrote a couple of functions of our own. We wrote read average, which returns the average of 12 readings, which we use to trigger the rest of the code, and read input, which is just one reading. Our second sensor was a load cell. We used the HX711 ADC in conjunction with the load cell in order to get readings from this. We used the HX711 library as well as writing our own code in order to use this in the way that we wanted it to. We needed a specific tera value for the load cell, and so we created a function that will load the tera value from a file located on the Raspberry Pi Pico. The value of the tera value is the value of an empty hopper. Read average works similarly to the ultrasonic, where it takes the average of an inputted number of times. Our actuator was a DC motor, which we coded to turn based off of the encoder position. So we'd input a certain number of degrees that we wanted it to rotate. It would turn that number of degrees and then stop. The number of degrees was calculated by encoder pulses.
Here I am talking about the power supply. The Jock power supply converts the voltage from the wall into a usable voltage for our project. The motor will run at max 7.5 volts, so we set our voltage to be about 6.6 volts. To adjust the voltage, you would need a small flathead screwdriver and turn a knob on the power supply. Here is a side-by-side comparison of the CAD and the physical device. Note the ultrasonic holes were moved from being on a separate piece to beneath the slider. However, when it came time to print, we just forgot to remove the wall of where the ultrasonic used to be, so that's why that wall is still there in the real life part. How it works. So here I'll talk about how each component works. The ultrasonic uses the USonic library from Lab 3 in order to read the data from the ultrasonic sensor. It would take 12 inputs and compute the average, and when that average is below a predetermined threshold, it will spin the motor. The load cell uses Adafruit's HX711 library for data processing. We will determine weight by comparing it with the load of the empty hopper. Then that current weight would set the state of the LED indicator. Now for the motor, as previously mentioned, our project is powered by a 12-volt power supply into a Jock power supply set at 6.6 volts. This powers the motor movement, which is triggered by the ultrasonic sensor and has its distance determined by the movement of the encoder. This ultimately dispenses food by spinning the crank arm and dropping it into the bowl. The main code constantly checks for whether or not the distance threshold on the ultrasonic sensor is broken. Once it is broken, the ultrasonic sends a signal to the DC motor to spin and dispense food. After that, the load cell will read its value and determine whether or not the inventory is low and if it should turn on the LED. Lastly, the motor will spin back the same amount of distance and the cycle will repeat.
So a quick demonstration behind the project. We can see that as the bowl is being sensed in front of the ultrasonic sensor, the mechanism continues to work. However, the left video demonstrates that the motor only spins when something is detected, to where it doesn't spin when it's taken away right here, and then it continues back to its mechanism when it's put back. And then this right hand video, there's an LED on the right hand side that turns on, which is an indicator for the user that the inventory is low, as the load cell is measuring how much more is left in the tank. And so in conclusion, the overall project was a success. All the requirements for ME106 and 154 were met, and we were able to present a fully functioning prototype on the day of the presentation. Some future improvements me and my group wanted to touch on was creating a steeper slope for the hopper, as we saw that not all the food was sliding down very efficiently when the food was running low. Smaller sliders, as we felt the links were a little bit too upsized compared to the actual body. Expanding the area for electronics, as our electronics were kind of just lying around and the original box that we designed couldn't necessarily fit because of the wiring. Taller bowl area, as the bowl, we know that all generic dog bowls aren't necessarily built like the container that we use in the presentation, and potentially adding an external clock or a timer or a remote, so that whenever the user needs to be away, they can, and they don't have to be there in person at all. And so this concludes our presentation. I hope everybody enjoyed, and I thank you for everybody's undivided attention. Thank you.